Okay, I suppose we'll get going. So I guess quick announcements. I have posted the quiz thing for submission on Blackboard. So this is something I forgot to mention for quote unquote quiz one, where it was, submit it, you get one. You can hand it in to me physically, or you can submit it on Blackboard. So something that is sort of a downside to handing it in to me physically is Blackboard will scream at you that you've missed a due date until I put grades in. So if you want to avoid that, what some students will do, if you hand it in to me physically, you just go into the Blackboard submission and you just say, handed it in to you in class. And then it won't nag you saying you missed a due date. Because that can be stressful, right? Like you go there and you're like, oh, what? I missed a due date? And it's like, no, you handed it in to me physically. I have it. It's just, it's due on Saturday at midnight or 11:59. And, it's Monday and I'm still working on grading them. And you're like, oh, God, did I screw it up? It's like, no, I'm still just on my desk, right? I'm still going through them. So it can help if you don't care, then fine, whatever. You don't have to do it, right? But if you're like, oh no, seeing that is stressful, just put anything in there. Just say, handed it in to you and click submit, right? It's not going to affect your grade. So that'll stop the nagging. The other thing is I put in, it's at the top on the front page. It's like a group list submission or something like that. So that's for you to let me know what groups you want to work in, like who's in your group, up to 4 students, including yourself. You can work alone. That's totally fine. I made it worth 1 point out of 1. It does not go towards your grade at all. It's just if I put it worth 1 point, then Blackboard will nag you about it. Now it does that when I want it to. It'll just be like, hey, you have a thing that's due, submit it. Again, if you don't do it, you're not going to lose marks or anything at all. It'll just be like, I'll send you an email and I'll be like, hey, are you working by yourself or are you with some people and just forgot? Like, what's up? It's so that when I build groups in Blackboard, it's easier to like assign things to you and grade and that sort of thing. So you have a question?
Yeah. So does just one person from the group just have to submit it? Or
yeah. So yeah. Well, it doesn't matter either way. So if you all submit it, I'll notice it. Like I go through the submissions and then pick all the names together and build a group. So if you both submit it, then I'll just be like, oh, that's the same group. So it's fine either way. So once the submission date passes, I hide this one. So if you don't submit, it won't nag you. So it won't do the same thing as the quizzes where, because you don't need to see you got 1 out of 1 because again, it doesn't affect your grade, so it doesn't matter. Okay, so we're gonna get moving along. So like I said, I do a format of like I lecture for a full class and then I do like half a class and then I give you a worksheet. So the worksheet's already posted on Blackboard. You can click it to see it if you want. I'll usually put the worksheet up on here too. So if you didn't bring your computer, don't worry about it. And if you did bring it and you're like, well, it's not out, don't worry about it. I'll put it up here. And then the quiz is on paper. I did not intend to print it on long paper. Have you ever had a day where you're like, this Monday sucks, and then everyone's like, Travis, it's Wednesday, and you're like, oh no, that's me today. So I didn't intend for it to be long. Sorry, it is. It just happens sometimes. So I'll hand that out when I'm done doing my spiel, and then it will be based on what we're going to talk about today. So last class, I did an introduction to logic and operators. So we just had mostly definitions, and a lot of it is stuff that sort of fits in with intuition or quote unquote just regular logical thinking, right? We just made it maybe a bit more formal. We had these operators, negation, which just works like a negative, right? Flips the truth value. And this is true when both are true, or this is true when when at least one is true. This is inclusive or. So if we wanted exclusive or, I would indicate it specifically that we're talking about that. Conditional, this was the weird one. Think about it as a promise. Today we're going to talk about truth tables. So that understanding of it will be way less important because now you have a truth table and you can be like, oh, for doing calculations with it, I just look at the truth table, right? That's the only thing you really need to know. And then we had this biconditional where I kind of finished at the end of class. So I did actually forget to write when is the biconditional true. It's true when P and Q have the same value. So if P is true and Q is true, it's true. If P is false and Q is false, it's true. So it's basically behaving like equality, right? If the two things are equal, then we say it's true. If they're different, we say it's false. So this is going to be important for basically that, right? Equality. That's what fits the role. Okay, so I sort of mentioned it in passing in class last time, but there's a better way to sort of collect all of this information, right? Rather than having to remember, okay, and is when the first thing is true and the second thing is true, then the whole thing is true, and yada, yada, yada. We have something called the truth table, which just sort of collects all of this information in a more condensed form. So we can build a truth table to more compactly explain when these operators are true. So the basic format, let's start with the simplest one, right? Negation. So it looks sort of like this. It is a table. Along the top, you have essentially your inputs first, and then you slowly build up to the statement you're working on. So in this case, we've got one input P, and we want to know what is the value of not P based on that input. So this truth table is pretty straightforward, right? We just have P, okay, if I plug in a P, what's not P going to be? Well, P can be true or it can be false, right? One or the other. Well, if P is true, we know negation turns it to false. And if it's false, negation turns it to true, right? So we can already kind of see that this is like a nicer way to collect the information, right? It's sort of just, if you know what P is, you just sort of draw a line through the table and that will tell you exactly what the operator is for that situation. So it's nice, handy, tabular form for collecting data. I did sort of mention this as well, and you can do whatever you're more comfortable with. So we've got T and F corresponds to 1 and 0, right? So you can write truth tables in binary if you would like. And that might help it make more sense, or it just might be easier to read or write. It's easy to write a 0 compared to an F, that sort of thing. I'll accept either. You can do whichever one you're more comfortable with. I don't care. I think most people, depending on, it's that thing, if you have programming background, you're going to be like, okay, yeah, sure, I'll do that. If you have none, you'll probably be like, whatever, it doesn't matter, and you'll just do the true false, because that's the one I usually do in examples, so that's the one that people usually do. Okay, so let's maybe work on something more complex, right? This had one input. What about two inputs, right? Well, we do kind of the same thing. But now if we have two inputs that can have two different values, so P could be true or false, Q could be true or false, we get a table that has 4 total possibilities. What about two inputs, P and Q, or say P and Q? So again, this is the English word and, this is the logical operator and. Well, we can kind of do the same thing, right? So we start by writing down our inputs. So what do we got? We got P, we've got Q. And then next to that, we write, well, what statement are we working with? P and Q. That's what we're trying to figure out the value of. So what values can P take? True or false, right? Now, we can also say what values can Q take, true or false. Don't write this down because I'm going to write it in a more cohesive way. But notice, this is true, true, false, false. What about false, true, and true, false? Right? Those are also possible, right? P could be true and Q could be false. So especially when we get bigger tables, one nice way to write these down is sort of like a pattern like approach. And you can start it either true, false, true, false, true, false, true, false, alternating all the way down and then sort of build up. Or you can start like this. And I'll give examples of both. You could also say, okay, well, I know that for every true value of P, Q can either be true or false. And so true, true, and then true or false. Well, now P can be false. And for both of those, Q can be true or false, right? So the important thing here is there's no repeated things here, right? True, 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 false, false, true, false, false. And we've got 4 of them, right? 2 inputs, 2 choices of values. That's combinatorics. If you remember it from high school, counting, stuff like that. We'll talk about it more later. We should get 4 possibilities. So you don't have to follow this pattern, by the way. You could just write them down however you want. And as long as you have, in this case, 4 of them, and they're all distinct, then you're fine, right? Then you just logic your way through it. So in this case, we're trying to figure out what's P and Q. Well, when it's true and true, that's the situation where this statement is true. P and Q is true when both P and Q are true. This is false, right? One of them is false. So the logical AND operator is false. Same thing here. And both of them are false, which means one of them is false. So we're done, right? And so now we can kind of see here that this is collecting the information in sort of like a tabular organized. Oh, yeah, question?
Well, once you.
Oh, I mean, I was just going to say this is like a more organized way of collecting it, especially when we start getting more complicated. So if we start adding 3 or 4 inputs, then you seeing it in a table rather than trying to remember everything is easier.
I was actually just going to ask something related to that, and it was, can any of the inputs be statements themselves? Like if you have P and Q and R, can one be P and Q and R, and then the answer be P and Q and R?
Yes. So we can use this to construct truth tables for more complex statements, and that's we're going to get to that. So first, I'm going to build the truth tables for all the operators, and then we can use this sort of to motivate us to say, okay, well, I have a very complex statement. Can I use this same format to figure out the truth value of that more complex statement? So I didn't give myself enough room here, unfortunately. So I'm just going to write it over here. I'm just going to write down the truth tables for all of the operators. And if you're working on this quiz and worksheet, this is probably like the one thing you're going to want to like put on a separate sheet and be like, all right, I'm just going to put that in front of me. It's going to make it way easier. So this is the truth table for all operators we've discussed. So just to demonstrate right here, I did TTFF on P and then TFTF. I'm going to swap that. That's totally fine too. So we've got P here. We've got Q here. So these are our inputs. Personally, this is the one I like more because I write down alternating T's and F's. And then what do I do next? It's sort of alternating. But now I write twice as many T's as before, right? So now I wrote 2 T's and then 2 F's, and I just do it until I have 4 of them, right? And that will make sense when we build a bigger one, when there's 8 or 16 inputs, you can kind of see the pattern. Okay, so there's the one we just did. So this was true here and false everywhere else. We've got P or Q. So this is only false in one situation, when they're both false. Otherwise, it's true. And then we've got the conditional. So this is that weird one where it's only false in one situation, and it's when you break a promise. So when P is true and Q is false, was when this is false. Otherwise, it's true. And the last one, the biconditional, or essentially equality operator, it's true when they're the same and false otherwise. So right here, they're both false. So this statement is true because they're equal, right? They're the same. Here, they're both true. It's true. They're the same. They're not the same. They're not the same. So we would say it's false. Okay, so the nice thing here is, as I was kind of indicating, there is a truth table for every statement, no matter how complex it is, right? It does not matter how many inputs you have or how complicated it is. You can make a truth table for it. So every statement or formula, I'll write both. Formula has a truth table. So we can ask ourselves, okay, well, how big are these tables going to get, right? That's always, I mean, when you're thinking about computers, it's a good idea to always keep in your mind, okay, well, how big is that though, right? If you're reading in a file and it's pretty simple, you're like, okay, well, you know, whatever, it's a list of names, right? It's a CSV file. It's got names of phone numbers and email addresses in it. How bad could that be? Suddenly there's 2 million entries in it. It's a lot of space, right? So we should be keeping in mind, well, how big is this going to be? But the other reason we should care in this case is to make sure we have it right, right? Did we write down everything? So we just have to think how many in a truth table. Well, that first one we had, it was just P, one input. It had 2 rows. This has 2 inputs, 4 rows. If we had 3 inputs, how many rows do you think we should have? So that's adding to, when we're talking about stuff like this, we're usually doubling. So it would be exponential, so it would be 8. That's a good instinct, though. You thought 2, right? I mean, this is, sorry, this lets me talk about something in math, like patterns. Oftentimes when we're trying to spot patterns, this is a good trick, is I said spot the pattern after 2. Well, that's not very much data, right? So saying 6 is not technically incorrect either. That's a good, based on the evidence you've seen. But the reason why it's 8 is a counting argument. So if we think about this, if there's 3 inputs, so P, Q, and R, each of those has 2 choices, right? So there would be, so let me say this. We have P, Q, and R. So there are 2 choices for P. There are 2 choices for Q. And then there are 2 choices for R. So if right here we have 4 choices total, right? If we ignore this, right? Because that's just this. We have 4 choices total, right? Now for each of these situations, we get another 2 choices, right? So here we'd get 2 choices. Here we get 2 choices. Here 2. Here 2. So that means there's 8 total, right? So it's 2 times 2 times 2 choices, which is 2 cubed, or 8. So that means the formula here is for n inputs, we have 2 to the n. For n inputs, 2 to the n rows. Now, in terms of me making you write on physical paper, we're never going to go past 3 because that would just be cruel. You would need a sheet that long, basically, to work with a truth table that big. So you're not going to have to worry about 16 rows or 32 rows or anything like that, just because it would be cumbersome. But the formula still stands, right? It's a counting argument. But the reason why I mention this is, let's say you're building a truth table and you look and you count and you're like, wait, there's only 7. That means you missed one, right? So that, just keeping this in mind, okay, I should have 8 total rows. You can just count them and make sure you have 8. And if you don't, then you go, okay, well now I have to begin the troubleshooting step of figuring out which one I missed, right? And that's just going through the motions. Okay, so let's try to build a truth table for a more complex statement. Let's build the truth table for, what do I have in the notes? P and Q or not R. So we see we have 3 inputs. So this table should have 8 rows. Oh, sorry, we can ask another question.
I was just gonna ask if you do have like, I guess more than 2 inputs, in this case, an odd number of inputs, can you take the 4 results of a truth table using 2 and use that as one row of inputs in a different truth table?
That's essentially what we're going to do. You could do that. But what I'm going to do is I'm going to sort of collect all the information into a single table so you can just kind of go through the motions. So let me show you what I mean. So we've got 3 inputs here, P, Q, and R. So when we're looking at this, we sort of have one big statement here that seems to be composed of 2 smaller substatements, right? P and Q, and not R. So that means if we want to figure out the blue part, the bigger part, then we just need to figure out what's P and Q and what's not R, right? So, okay, let's go ahead and start with our inputs, right? P can be true or false. So I do this in a sort of pattern-oriented way. You can just write them down, and as long as you have 8, you're okay. But I like to go true, false, true, false, true, false, true, false. I know there's 8 rows, right? So I just stop now, right? I've written down 8 true or false statements. Now, I sort of make a note here. I'm doubling the amount of T's that I write, and I'm doubling the amount of F's. So we could just do this sort of pattern, TT, FF, TT, FF. And then the next thing we do is we double it again. Now I write 4 T's and 4 F's. And now we just look. Do we have any duplicates? And we captured everything, right? We've got 8 total. True, true, true. Okay, good. F, true, true. That's not the same as the first one. TFT, those aren't the same. FFT, those aren't the same. TTF, not the same. FTF, TFF, FFF, right? So this sort of alternating pattern let us write down everything without having to think about it very much. Again, you could just try to write them down from memory, but I think just writing it down in sort of a pattern or algorithmic like way is nicer. But you're free to do it however you choose. Okay, so now we have our 8 rows that we need. So now, like I was saying, this is sort of a compound statement in a sense, right? We've got 2 littler statements, P and Q, and then we've got not R. So we can figure out what these 2 are. Then, if we just take this piece here, or this piece here, then that gives us the truth table for this, right? And that's why keeping this in mind is important, right? Because this P, I've said it's a formula, right? It's not just a single statement. It could be a formula, which means it can be much more complex than just P, right? So you can kind of think of this as, instead of just a statement, it's input 1 or input 2 gives these values under these situations, right? So if input 1 is true and input 2 is true, then we write down true, right? If input 1 is false and input 2 is false, we write down false, right? Even if input 1 comes from something much more complex. So let's sort of work this out, right? We just do it sort of piecemeal, right? So let's figure out P and Q. So we just look at P and Q. This row here, it ends up not mattering, right? We're only interested in P and Q. But we do still have 8 total things to go through. So P and Q is true when both of the inputs are true, right? We take a look here. Input 1 is true. Input 2 is true. We write down a true. Otherwise, we write down a false. So in this case, input 1 is true. Input 2 is true. Let's go ahead and write down a true. Input 1 is false. Input 2 is true. Well, we know we write down a false based on that table. Same thing here. True, false. We write down a false because we're dealing with the logical AND operator on these things. False, false. We write down a false. True, true. Ah! Now we write down a true again, right? False, true. Well, false because we're dealing with AND. True, false. False, false. Now you can kind of see here the fact that we wrote down in this sort of pattern-like way, we've essentially got the table twice, right? Which I think is kind of what you were saying, right? We're essentially combining two truth tables together. So if we cover this up, we've essentially got the truth table for P and Q, right? TFF, just like this. But then, right below it, we've got it again, right? We've basically just done the same work twice. But it's not complicated work, right? It's just, or we're just duplicating information, right? We're just kind of reading stuff and writing it down. Okay, so now our goal is to get not R, because if we know that, then we just ignore everything we've done. We only then care about this and this, because what we want to do is take the OR of input 1 with input 2. So let me just write this down. This is input 1. This is input 2. And we just found input 1. So now let's find 2. Well, this one's relatively easy, right? We just take this R column and flip them, right? That's what negation does. F, 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 true, 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 true. Right? We just take what's here and flip it, right? Okay, so now we have input 1, this part of the table, input 2, this part of the table, and now we just say, okay, what happens when I take the OR of them, right? So I just take a look at this. I got my OR here. Well, what do I write in every situation? If input 1 is true and input 2 is true, I write down a true. All right, so input 1 is true, input 1 is false. What do I write down? Input 1 is true, input 1 is false. I write down a true. Input 1 is false, input 2 is false. I write down a false. False, false, one's a false. False, false, I write down a false. True, true, I write down a true. False, true, that's a true. False, true. False, true. So once we've built these sort of pieces of the statement, this stuff here doesn't even matter anymore, right? We're just sort of, we're building from the bottom up, right? From the simplest statement on the left here, which is just P, Q, R, our inputs. And then we're sort of adding in more complex statements until we get to our final one, which we can then sort of essentially just combine 2 into 1, right? It's sort of this building from the ground up style approach, right? We're taking the simplest case and then, okay, the next step is a little more complicated. And then we just imagine, okay, like say this was part of another more complex statement after it, right? We'd say, all right, we got this one now. Let's unpack the next statement and do the same thing. And we say I just need to take this as my input 1, and whatever ends up over here is my input 2, and then I do the same thing, right? So you can just sort of unpack things this way. Now, truth tables are sort of the more mathy approach, but you can kind of think in terms of like conditional statements, right? Writing stuff like this is not uncommon, right? Input 1 and input 2, or the negation of input 3, right? So you'd say if something like this, then run my code. So just knowing when this is going to be true, it intuitively is important, right? Maybe the truth table is less important, unless you're doing something very complex. If you're working with something very complex with a lot of inputs, sometimes it can be helpful to just write down a truth table of what you wrote down. Just be like, why isn't this working, right? I expect it to work and it's not. And it could just help you, because then you might even look at this and be like, wait, that's not what I expected. That's not the truth table. It should be, right? It's supposed to be true in all but one case. And then you look and you're like, wait, it's false in 3 cases. This is the wrong statement then. Right? I want one that's true only in one case, right? So that's kind of the importance of it, is just it's sort of as like a logical thinking rather than writing down an actual truth table. Okay, so any questions on that before we just do another example, maybe? Okie doke. So I'm just going to do another one. But I'll go a little quicker. But if you have any, so this is true in general. If I'm going through something, you're like, hey, wait a minute, that part I didn't get. Just say, Travis, I didn't get that part. And then I can explain it. So that means, on the flip side, if nobody says anything, I just go, well, I assume it's fine. So let's build the following truth table. Suppose P of x comma y comma z is the following statement, formula. It's x plus y is less than or equal to z. So first number plus second number, is that less than or equal to the third number? So let's find the truth table for not P of x, y, z and Q or R. Okay, so we have this thing here, right? It's more complex, but it's still just a formula, right? It's still just P. So we can treat it exactly the same way, right? Yes, whether or not it's true depends on our choice of X, Y, and Z, but it's still either true or false, right? Then use it to find the truth value when X is 1, Y is 2, Z is 3, and R is false. So there's sort of 2 parts to this question. First, we have to build this truth table in the first place, right? And then it says, okay, well, find a truth value when some specific conditions are true. And we kind of look at this, we're like, hey, wait, we've got 3 inputs, and we only specified 2, right? Well, okay, technically there's the 6 inputs, but when we plug in X, Y, and Z, we get one truth value for the statement P, right? It's going to be a specific one. So we specified a truth value for P and a truth value for R, but what about Q, right? How are we going to rectify that? There's going to be 2 answers, right? Well, maybe not. Let's build the truth table. So we do the same thing. We put down our inputs first. So just like before, I'm going to do this pattern. TF, 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 TF. And then I double the amount of T's I write and F's. T, T, F, F, T, T, F, F. Double it again. T, 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 F, 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 F. So if you always start with this, with 3 inputs, you're already in good shape. It's like half the marks probably. Okay, so again, we've got not P of X, Y, and Z. That's our input 1. And then we have this input 2, Q or R, that we need to figure out. And then once we know that, we can use that to figure out the truth value of the whole statement. So this one, relatively straightforward. We just flip the signs, right? True becomes false, false becomes true. FT, FT, FT. All right, great. That one's not too bad. Q or R, this is true unless both inputs are false. So we're covering this up now, and we're just looking at this. So we've got true, 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 false. Right, because false, 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 false. And now we look at this compound statement and we say, okay, input 1 and input 2. So the AND operator is true when input 1 and input 2 are both true. Otherwise, we write down an F. There's an F here, so we write down an F, because again, we're dealing with this AND operator. T and T, write down a true. F and T, that's false. T and T, we write down a true. F and T, T and T. Hold on. I gotta draw some lines here. A ruler and straight edge helps. Okay, so F and T, false. T and T, true. F and T, false. T and T, true. F and T, false. T and T, true. F and F, false. T and F, false. Okay, so that's our truth table, right? Now we have to answer the second question, which says, okay, we care when X is 1, Y is 2, and Z is 3. 1, 2, 3. What does this mean? Well, it means 1 plus 2 is less than or equal to 3. 1 plus 2 is 3. So 3 is less than or equal to 3, so this is true. So, okay, P is true. R is false. So now we just take a look at our table here. When is P true? Here, 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 and here. Right, these 4 lines. When is R true? Here, 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 and here. Well, the only situations where they're both true is this one and this one. So line 1 and line 3. So we can just draw a dotted line through this whole thing. Bam. False. False. So Q doesn't matter in this case, right? Doesn't matter if Q is true or false, right? And we see that right here. We are in the situation Q is either true or false. Doesn't change the truth value, right? We still got false either way. So in this case, the statement is false with the given input.
Excuse me.
Yeah.
Can you please spell it again?
Which part?
P bracket 1 into the last one.
So this is saying that P of x, y, z is the formula x plus y less than or equal to z, right? So what this is saying is the first number goes here, second number goes here, third number goes here, right? So 1 plus 2, is that less than or equal to 3, right? In this case, it is, so we would say it's true, right? So that leads to a true statement. And then R is a false statement given to us, right? It says right there, R is false, right? So we just have to now draw on our table, where are those conditions true, right? Where is P true and R false? Right, so here and here. Okay. Oh, sorry. Q doesn't matter. Okay, so I have a couple of definitions here, and also there is a large number of what I'm going to say. Oh, yeah, sorry. Go ahead.
In lines 1 and 3, the R is true.
Yeah.
Yeah, that's just one option.
Oh. I think my brain flipped the T and the F, didn't it?
Yeah.
Wow. That explains why everyone is like, what are you talking about, Travis? Okay, yes, thank you. So again, we have P is true. We're going to need our colors here. So R is false, not true. So here, 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 and here. So the last 4 lines are where that's the case. So that means this right here, line 5, false. Line 7, false. So fortunately, it worked out still. I should just trust my notes. But we see here the same thing is still true, right? We draw these dotted lines through the truth table. We say, okay, P is true. R is false. Those are the situations we care about. What happens at the very end? And we see it doesn't matter what Q is. If Q were true or false, it wouldn't change our answer, right? Okay, thank you for actually reading what I write instead of me, who did not read what I wrote, apparently. Okay, so I have a definition real quick. And that's the idea of what's called a tautology, which is, this is logic terminology for equality, basically. A tautology is a statement that is always true, no matter what inputs it has. It's a logical expression that evaluates to true always. So it does not matter what inputs you put into it, it's going to be true. Doesn't matter. So this is the logical equivalent of equality. So an example of this I have in my notes, which we'll need them when we start talking about rules of logic, and I will repeat them then. I have a whole table of these sort of rules. So I'm just going to present a couple of them right here. So we have that P biconditional, not P, a tautology. So again, what that means is it's true all the time. But if this statement is true all the time, and I've sort of mentioned that this operator here behaves like equality, that means you can replace this statement with this statement, right? So if you have a tautology with a biconditional, so I'll write down, that's this double arrows, right? Then you can replace the statement on the left with the one on the right. The left statement with the right anytime you write it. So if we have this concept of, I see not P written down somewhere, and I'm like, hey, that means I can replace it with P, we're sort of starting to get algebra rules, right? This looks like, think in numbers, right? 1 is equal to negative 1, right? That looks an awful lot like that, right? Because it is, right? This is negation for numbers, right? The negative of a negative is a positive. This is saying the negative of a negative statement is the original statement, right? They cancel out, right? So let's see what this truth table looks like, just so we can do another example of a truth table, and then I will send you on your merry way to construct truth tables with me around to help. So let's take a look at this here. We've got P. And okay, what pieces do we have here? Well, we've got not P, right? That means we do not P, and then not P. And then finally, we need to do that big statement. This thing. So see how I'm sort of unpacking it here, right? We got the left-hand side here, which is just P. And then we got this other statement over here, not P. So I wrote down, all right, what's inside the brackets? Not P. Then that with the outside of the brackets, not P. And the whole big statement, right? All right, well, we've just got our P. That could be true or false. All right, not P. What do I write here?
False.
Yeah, it's just, we just flip the signs here, right? So this is true. All right, cool. On to the next statement. So we've got not P. So this is a bit weird, but this right here is our input, not P. So we just negate whatever not P is, right? So this is our input. So what should I write here? Yes, exactly. We flip this thing, right? We've got our input, not P, we flip it. So that means we flip this. Now, this right here is input 1. This is input 2 on the right to this sort of biconditional thing. Now, if we look at the truth table for, P biconditional Q, it just says if they're the same, we write down true, right? So we say, all right, this is input 1. This is input 2. So are they the same? True, true. False, false. They're the same. So this statement here is true no matter what, right? It just evaluates the true no matter what you plug in for P. So this is what we mean when we say is a logical expression that evaluates the true always. This is essentially going to mean final column in the truth table is all P, all the way down, the whole thing. So what that means then is anytime we saw this written down, not P, or -1, we can instead write down P, or 1. Right? You can cancel a negative by negating it again. And I mean, even when we think about like in terms of math or just English, right? Negating a negative cancels out, right? Okay, so with that, I'm going to put the quote-unquote worksheet up on the screen. I'll hand this out too. So now, I basically just set you on your merry way. Historically, some students are just like, okay, bye. They just get up and leave. I don't hold you hostage. If you want to do that and you're like, I'll just work on it at home on my own time, totally up to you. Usually, though, a lot of people stick around because they're like, well, I could just finish the quiz and get Travis to help me with it, so I'll do that. So whichever one you prefer, I'm okay with either. So just give me a sec, and I will pull up the worksheet, which again, it's just going to be building truth tables. And it's one of those things where maybe the first one you build is going to be slow, and you're going to be like, uh-oh. But then you do a few of them, and you're like, okay, I get it, right? That's the thing with math is it's never a spectator sport, which is why I try to do try not to do too much lecturing. Even in the lectures, I'll sometimes be like, okay, you guys do this one real quick. Just because if I just make you watch it, I took a lot of math. Even when I was a student in math, sometimes it was in one ear, out the other, until I sat down and tried the exercise myself, right? Once I did that, it was relatively okay. That computer is exceptionally slow, so I'm going to hand these out.
Is there an assignment and a quiz?
So the worksheet is just extra practice if you feel you need it. Actually more notes on that. So the worksheet is just extra practice. No, not for marks or anything like that. So if you're like, I just want more, you can do it. And I post the solutions to that. So you'll have the solutions to a bunch of exercises, right? Then there's the quiz, and that's the one that you're actually graded on. So usually people like to make sure that they're certain before they submit something. And that's the purpose of those worksheets. I'm just going to do this. I'm going to slap down a bunch and, except in this case, I don't think I'm going to make you watch that. So the worksheet I'm going to put up on the projector. Just to save some paper because nobody's going to hand over this. Right?
This one.
Oh, okay. I need to fix that. Easy to fix though. That's just that you copied the wrong file and tried to write it. Like I said, I'm having a Wednesday that feels like a Monday. Quite often. Go. You, well, I don't know, some number of them. I'll come grab the rest at the end. There you go. You don't mind it? Did I get you one? Question.
Did a Google sheet for now.
The quiz is on building and you're like one question.
Nice.
So I don't like giving homework. I don't like grading.
Fair enough.
Did everyone get one? Oh. You know what? I went that way and then I was like, yeah, I handed stuff down this road. No, I didn't. I'm having a real thing. That could be 2 there and then 1 for you. Okay, I'm gonna go fix the Google Drive issue. Oh, yep. What's up? So that's up to you. So this is when it comes to something like this that doesn't have quote unquote a lot of work to show. The more you show, the easier it is for me to see if you went wrong where. But if you're confident, especially because like basically what you're asking is like, hey, can I just do mitigation in my head? Right? That's totally fine. Up to you. Some people don't want to do it in their head, but if you're comfortable doing it in your head, go for it. Let's see if I can fix this.